Here's a stop sign. Any driver reads it in a heartbeat, and so does the vision model in a self-driving car. Now an attacker adds a few small stickers, a strip of black and white tape, placed just so. To you and me, it's still obviously a stop sign with some graffiti on it, but the model now reads it with high confidence as a speed limit 45 sign. Nobody touched the car, nobody breached the network. The attacker changed a few pixels of the world and walked the model straight across an invisible line it didn't know it had. That line is a decision boundary, and today we attack it 4 different ways: fooling the model, stealing the model, and pulling the model's secrets back out. And then we pair every one of those attacks with the defense that blunts it. Let me tell you where we're headed. By the end of this episode, you'll be able to do 3 things. First, name and tell apart the 4 classic adversarial machine learning attacks. Second, explain why a trained model is attackable at all, which comes down to its boundaries, its gradients, and the query access you hand out. And third, pair each attack with a concrete defense and locate the whole problem on the inference API. Remember the series thesis: SecAI Plus is security architecture for AI Plus framework fluency. Watch for the pattern today, because almost every defense lives in the architecture around the model, the API, the rate limiter, the monitor, not inside the weights. You rarely patch a model out of these problems, you wrap it. And one scope fence before we start. These are all inference time attacks on a model that's already trained. Train time tampering, poisoning, and backdoors, that's episode 8. The LLM specific input attack, prompt injection, that's episodes 6 and 7. Today is the classic adversarial ML quartet. So why is a trained model attackable in the first place? Start with what a classifier actually does. Its whole job is to carve the input space into regions and draw decision boundaries between them. Cat versus dog, fraud versus legitimate, malware versus benign. Those boundaries are high-dimensional, they're jagged, and the model is most uncertain right next to them. So an attacker's goal is simple: find the shortest nudge that pushes an input across the nearest boundary. How do they find that nudge? With gradients. During training, the model uses the gradient, the direction that most increases an error, to improve itself. Flip the sign, and that very same gradient tells an attacker the direction that most breaks the model, the smallest change to the input that most increases its error. The math that builds the model also tells you how to fool it. And the thing that makes all of this practical is query access. Every model you expose, an API, a web form, a download, is a machine an attacker can interrogate thousands of times. Send an input, read the output, adjust, repeat. Even with no gradients and no peek inside, what we call black box, enough query and observe loops will approximate the boundary, then the gradient, and eventually the model itself. Hold those 3 together: boundaries, gradients, and query access, because each of the 4 attacks is just a different thing an adversary does with them. One thing worth flagging for the exam: sort the 4 attacks by what they violate. Evasion is an integrity attack. It bends the model's decision at runtime. Extraction, inversion, and membership inference are confidentiality attacks. They steal the model or its training data. So if a scenario is about a wrong answer on purpose, think integrity, think evasion. If it's about something leaking out, the model, its data, or who was in it, think confidentiality. The control follows directly from the column. Let's take the first attack, evasion, fooling the model at runtime. Evasion is the stop sign attack. The model is fixed and trustworthy. The attacker crafts an input that looks benign or completely unchanged to a human, but lands on the wrong side of a boundary. Think spam shaped to read as ham, malware perturbed to score as benign, a face patch that defeats recognition, or that taped stop sign. The crafted input is called an adversarial example, and producing it is MITRE Atlas's craft adversarial data technique. The perturbation can be tiny, imperceptible pixel noise, or it can be physical, stickers and patches. The point is that it's designed against this specific model's boundaries. It isn't random. The classic picture is a panda image, original classified panda. Add a faint layer of structured noise, and the model now calls it a gibbon at 99% confidence. The human sees one image, the model sees 2. So what is an evasion attack? It's when an adversary feeds a trained model a carefully crafted input, an adversarial example, that a human would read normally, but that the model misclassifies. The model and its training are untouched. The attack happens entirely at inference time, by exploiting the model's decision boundaries to push one input across the line on purpose. Now the other three attacks, stealing the model and its secrets by querying. These all run the same play. Query, observe, reconstruct, but they aim at different prizes. Picture the diagram. The attacker sends many crafted queries into your inference API, reads the outputs, and rebuilds something from the answers. First, model extraction, or model stealing. Here, you treat the model as an oracle, send a large, well-chosen set of inputs, record the outputs, and train a substitute model on those input-output pairs. With enough queries, the clone approximates your model's behavior. Now they have your intellectual property for free, plus a private copy to craft evasion examples against offline. And returning raw confidence scores makes this dramatically cheaper. Second, model inversion. Instead of copying behavior, the attacker reconstructs inputs. By probing how confidently the model responds and optimizing against it, they can recover a representative example of a class, famously recovering a recognizable face from a facial recognition model that was only ever supposed to output a name. Third, membership inference, the narrowest and often the most damaging leak. Here, you don't reconstruct the data at all. You just ask, was this specific record in the training set? Models tend to be more confident on data they memorized, so a yes or no on membership is recoverable from the outputs. And when the training set is patients in the oncology study or users in the breach corpus, membership is the sensitive fact. That's squarely OWASP LLM02, Sensitive Information Disclosure. Frame all three the same way. Their exfiltration through the front door. MITRE trace names that surface directly. AML.T0024, exfiltration via ML Inference API. The attacker never needs to breach storage. The prediction endpoint is the leak channel, one query at a time. So what is a membership inference attack? It determines whether a specific data record was part of a model's training set without ever seeing that training set directly. The attacker exploits the fact that models behave a little differently, often more confidently, on data they were trained on. And even a yes or no answer can be a serious privacy breach when being in the dataset is itself the secret. Now let's pair every attack with a control. The shape of each defense follows from the three enablers. You can't delete decision boundaries or gradients, so you harden the model where you can, and you govern query access because that's the lever you actually control. Start with robustness, which blunts evasion. That's adversarial training, where you train on adversarial examples so the boundaries sit farther from normal inputs, plus input preprocessing and sanitization, plus ensembles. It raises the attacker's cost. Treat it as risk reduction, not a cure. Robustness is an arms race, not a patch. Next, rate limiting and query monitoring, which blunt extraction, inversion, and membership inference. Every one of those attacks needs many queries. So per identity rate limits, quotas, anomaly detection on query patterns, watching for high volume, boundary probing, or systematically space-filling inputs, plus authenticated access. All of that turns a quiet offline attack into a noisy, throttled, detectable one. Then output minimization, which starves all of them. Return the least the use case needs. Labels instead of full confidence vectors, rounded or coarse scores, suppress per class probabilities. Less signal per query means more queries needed, which makes rate limiting and monitoring bite even harder. And for inversion and membership specifically, add privacy-preserving training like differential privacy, so the model memorizes individuals less. Finally, monitoring and detection, which catches what gets through. Log and baseline your inference traffic, alert on the query signatures we just described, and watch for a single principal slowly reconstructing your model. This is your manage function in the NIST-ARM sense, operational oversight of a deployed model. And notice where every one of these controls lives. the API gateway, the rate limiter, the logging pipeline, the training recipe. That's the architecture around the model. The model is the asset. The protection is the system you build around it. One more thing worth flagging for the exam. The common thread across all of this is query access, and the highest leverage defenses, rate limiting, output minimization, and query monitoring, are exactly the ones that don't touch the model's weights. So if a question asks how to defend against extraction or inference attacks, favor controls on how much the API reveals and how often it can be asked before you reach for model internal fixes. Restrict the queries, restrict the leak. Let me leave you with 3 takeaways. 1. Adversarial machine learning is 4 attacks on a trained model. Evasion bends its answer, that's integrity, while extraction, inversion, and membership inference steal the model or its data, that's confidentiality. 2. They're all possible because of decision boundaries, gradients, and query access, and your strongest lever is the one you own, the query. 3. Pair every attack with a defense, robustness for evasion and rate limiting, output minimization, and monitoring around the inference API, which MITRE Atlas flags as AML.T0024. Next up is Episode 6, Prompt Injection 1, Direct and Jailbreaks, where the attacker stops crafting pixels and starts crafting words, feeding instructions straight into an LLM. If this helped, subscribe and drop a question in the comments. That's the architecture lens. I'll see you in the next one.